Do you hear me or not?
Yes.
Okay. Specialists in p-Adic analysis are my collaborators, Alexander Bendikov and Alexander Grigoryan. I believe that those names are well known for you. My area is physics and mathematics of the random environment, random media theory, and especially one of the essential parts of the random media theory is the theory of random operators. And I will discuss today Anderson model, Anders type model, where instead of the usual Laplace operator, lattice Laplace operator, or continuous Laplace operator, we consider hierarchical Laplace operator. From my point of view, hierarchical Laplace operator or p-Adic Laplace operators are some kind of the superfractals. They have so high level of the symmetry that the spectrum and the eigenfunction are very simple, and as a result, it's much easier to study perturbation of such operator by the random potential. But I want to formulate briefly what is the classical Anderson model and what are the problems related to the Anderson problem. Anderson and Mott received Nobel Prize for the pioneering work in the theory of disordered materials, disordered metals, theory of conductivity of disordered metals. And one of the classical model can be formulated in the following form. We have lattice ZD, we have space A2 of ZD, and Laplace operator on the lattice. In the simplest form, we can define then summation psi of x prime over x prime such that distance between x prime and x is equal to 1 minus 2d psi of x. This is the lattice Laplace operator, and let's consider now Hamiltonian H psi, which is the Laplace operator. This operator is negative, but I can write down here minus, but it's not very essential because operator delta on the lattice is bounded, plus sigma v of x omega times psi. This is a Laplace operator. It will be defined in L2 because delta is bounded. V of x omega are random variables, assume that they are IID random variables, and for instance, uniform on the interval -1 plus 1. And sigma is the level of disorder, some positive constant. If sigma is large, it's very random Hamiltonian. For small sigma, we have a forced transition to the Laplace operator if sigma tends to 0. This is the self-adjoint operator in L2 small. The question is, what can you say about spectrum of this operator? And on the physical level, Anderson proved that for large sigma, if sigma is greater or equal some critical constant, will depend on the dimension d, but in fact, dimension d must be greater or equal than 3 For large enough sigma, this operator has complete system of the exponentially decreasing eigenfunctions. There is complete system psi n of x. Of course, because potential is random, omega is the realization of the potential, this system is also. V of x omega are uniformly distributed random variables on the interval 0, 1.
Okay, that's fine now.
And sigma is coupling constant, label of disorder. And for large sigma, Anderson proved at spherical level that span of eigenfunctions is a full L2. It means that in this case, the spectrum is pure point. But set of corresponding random values lambda n of omega, if you consider closure of this set, it will be interval from minus sigma minus 4d to sigma. It means that it's the spectrum. This is the spectrum of the Laplace operator from minus 4d to 0. And it is to make the spectrum a bit wider at the distance sigma on this coupling for this elementary fact. This is for large sigma, but for small sigma, even critical, according to Anderson, we have coexistence of two types of the eigenfunction. True eigenfunctions, which are exponentially decreasing, and so on and so forth, which they correspond to the lambda, which are close to the bottom of the spectrum, and somewhere inside spectrum of Laplace operator, we have absolutely continuous component of the spectrum. This is what was written in classical physical papers. In dimension 1 and 2, according again to the Anderson and Mott especially works in one dimension, we can expect the pure point spectrum for arbitrary sigma, small and lambda. If we have pure point spectrum, according to physics, that means that we have phenomenon of localization. It means that propagation of the electromagnetic waves in this medium is highly suppressed. There is localization of the waves. It means that metals with high level of disorder have properties similar to the amorphic insulator states. But at the same time, for low level of disorder, according to Anderson, but maybe there is absolute continuous part of the spectrum, and it indicates that bad metals can be used for electric conductivity, and this is a fact of reality. Of course, all real materials are disordered to some extent, but nevertheless, we have wires, we have transmission of the electric current, and so on and so forth. This is the Anderson model. And mathematician proved the first part of this conjecture, that for large sigma, for sufficient large sigma, there is complete localization, there is pure point spectrum with exponential decreasing eigenfunctions. And not only for such operators, but even for more general non-local operator, we can consider local operator, the tilde psi of x, the summation over z belongs to lattice zd, psi of x plus z minus psi of x times a of z. This operator, in fact, is a generator of symmetric random walk on the lattice z. But Laplace operator, of course, is a generator of the Brownian motion on the in RD. But if, for instance, if A of z, which must be positive and symmetric, satisfy estimation constant over 1 plus absolute value of z to the degree d plus epsilon, they are decreasing very slowly, very close to the threshold when we have divergence of this series. Then in this case, again, for large enough sigma, operator delta tilde plus sigma u of x omega has pure point spectrum. In this case, of course, eigenfunctions are not decreasing exponentially. In particular, instead of delta tilde can be some fractional power of the Laplace operator. This is for the latest Laplace operator. Situation with continuous Laplace operator a bit more complicated, and still there is no significant result in continuity except the fact that for low energies near the bottom of the spectrum, we have pure point spectrum for some classes of the potentials, which I don't want to discuss. I will consider later on hierarchical Anderson model based on the ultra metric spaces, which have many properties for which Laplace operator is non-local and has many properties of the discrete Laplace operator, even in the situation where the phase space is continuous. This is Anderson conjecture. Repeat once more time. For large coupling constant, localization is proven. For small coupling constants, information equals to 0. And there are many attempts. What is going on in dimension 2 completely is not known, except, of course, case of the large sigma. It is not known. There is no agreement between physicists what we have for small sigma, absolute continuous part, or maybe some other spectral bifurcation. This is open question. In dimension 1, theory is complete. We have localization and so on and so forth. In attempt to get some progress in the Anderson conjecture, it was very natural to study the Laplace operator on the graphs, and especially graphs which have some good self-similarity properties, for instance, of the fractal lattices like Sierpinski lattice and so on and so forth. And there are some results in some for some fractals, for instance, for Sierpinski lattice, which I do not want to discuss in details. We have results on the pure localization dimension of such operator, spectral dimension of such operator between 1 and 2. This is probably indicates that for dimension at least between 1 and 2, greater than 1 but less than 2, we have localization, pure localization in the wide, in the very wide situations. But let us I want to formulate now the localization problem for the random under the model in the ultra metric space. And I will write down some formulas now. Formulas, in fact, are, of course, similar to the formulas which Kochubey used in the previous talk, but nevertheless, I will not use p-Adic language completely. I will define some integral operator in L2 of 0 infinity. You have space X, half X is 0 infinity, and we have L2 of X dx with respect to index measure. And on this, in the L2, we define some Laplace operator in the following form: L psi of X operator L we will define in terms using some ultra metric, namely consider family of the partitions of 0 infinity on the intervals of the form I minus 1 2 to the power r I to the power r. I here 1, 2, and so on and so forth. Intervals, this is closed on the left and open on the right. And now here, rank of such operator can be arbitrary integer 0 plus minus 1, and so on and so forth. And each point X on the lattice covered by one interval of each rank I R X is the interval of the length to the power R, single interval containing point X. I will denote this interval I of R sub I. And IR of X is the interval of the rank R containing X. And after this, we define the operator L. We can define matrix U of X, Y is 2 to the power N of X, Y. X is not equal to Y. This is a p-Adic model. Essentially, one of the versions of the p-Adic model goes to Dyson. Dyson introduced similar operator and similar partition and similar metrics when he studied Ising type of phase transition for the one-dimensional ferromagnetic with long-range, slowly decreasing potential. It's famous paper. 0 of X is equal to 1. And N of XY is simply minimal R such that the interval of the rank R contains both point X and Y. But 2 point X and Y can be very close, but of course, corresponding number can be, in fact, very large. So for instance, if we consider point 0 and point 2 to the power R, which is here, then distance between this point and this interval 0 to r, this distance, which very small in Euclidean sense, is very large, is non-Archimedean metrics. This is ultrametric, and if we equip zero infinity with this ultrametric, it will be complete locally compact, non-compact space, separable, and so on and so forth. But Baret sigma algebra and measure is the standard Lebesgue measure. And after this, we defined operator LPCSS by the formula. It has to fix some constant kappa between 0 and 1. And after this, we have summation r from negative infinity to plus infinity. Here 1 minus kappa to the power r. And here we have projector rank 1 operator, which is equal 1 or 2 to the power negative r, integral over interval of the rank r containing given point x, psi of y dy. This is the mean value of function psi of this interval and minus psi at the point x. This interval is the elementary projector, orthogonal projector in L2. And after this, we consider combination of such elementary projectors with this geometrical weight. Let us know that for positive r, weight decreasing very fast, but for negative r, weights are huge, but they can be compensated by the fact that 1 or 2 to the power r, negative r in this case, will be very small for negative r. This is small constant. This operator is non-positive, and it's well defined on the function which completely supported in the sense that function psi, for instance, is locally constant on the finite system of the intervals of our partitions. This operator symmetric, non-positive, and spectral theory of this operator is trivial. Namely, if you consider the interval I minus 1 to the power r, I to the power r, interval which I called I sub r I, and on this operator we can consider such function containing positive bump and negative bump, and height of this bump will be, for instance, it will be 2 to the power negative r over 2, and symmetrical with the same constant with minus. This is the classical Haar function. Haar function concentrated, completely supported on the interval I sub r I. And such a function, Haar functions, it's orthonormal basis. And all such functions are eigenfunction of our operator, namely L I sub r I equals kappa to the power r times chi with sign minus. And the Kochubey-Tok operator was defined differently in terms of the on the field Q sub p, field of p-Adic number, but nevertheless the central relation was the same. We have here infinite system of negative eigenvalues for very negative r, because kappa is less than 1, they are highly separated, and each eigenvalue has infinite multiplicity. This is a spectrum of Laplace operator. It's very high multiplicity of eigenfunctions. This is a manifestation of the very high level of the symmetry of our Laplace operator. If you consider this Laplace operator on the finite interval, the length to the power r, and again, for this restriction of L on this finite interval, you will find eigenvalues. Spectrum in this case will be discrete, and it's possible to define so-called integrated density of state for the Laplace operator. Let us consider interval of the length to the power r and n sub r times number of lambda I, which are less than lambda. This is n sub r of lambda. This is the counting function of the discrete spectrum divided by total by the length of this interval. Passing to the limit, we will find that n of lambda converges to some limiting function. This limiting function will be concentrated on the point minus kappa to the power r, and it's will converge to n of lambda. And if you consider n of, this is for negative lambda, but n of minus lambda will be, for large lambda has asymptotic, roughly speaking. There is no exact asymptotic, but lambda to the power s over. It means that spectrum of our operator in the finite big volume has approximately power asymptotic for large energies lambda, and S is the spectral dimension. S dimension. This is the spectral dimension of this ultrametric space plus Laplace operator given on L2 on this space. And this spectral dimension in this case will be equal to logarithm 2 divided by logarithm 1 over kappa. If kappa is small, that dimension is close to 0. If kappa close to 1, because kappa between 0 and 1, if kappa is close to 1, then in this case, the logarithm will be close to 0, and spectral dimension will be very large. If we have self-adjoint operator, which is in fact is self-adjoint and non-positive, then we can construct a Markov process, which we can call hierarchical Brownian motion S of t. This continuous time t, which corresponds to the operator L. I will write down L sub kappa. We have dyadic Dyson type system, and the operator contains parameter kappa. Spectrum of this operator is negative and consists of the different powers of kappa with minus, and pt of xy is transition density of this process T for with respect to Lebesgue measure. For fixed x is the initial point of the Markov process, y is the point where process must be at the moment t, and this p of t xy can be presented as the usual Fourier expansion with respect to system of eigenfunction. And And in this case, elementary analysis shows that PTXX on the diagonal, there is no exact asymptotic, but there is rough asymptotics, 1 over t to the power kappa s over. S is the spectral dimension. And if spectral dimension is less or equal than 2, then the integral of pt xx, and this integral, of course, due to high level of symmetry, is independent of x. This integral from 0 to infinity will be equal to infinity. It means the process is recurrent. And for spectral dimension which is greater than 2, we have transient process, a process which goes to infinity for given initial point p almost surely if time t goes to infinity. S greater than 2, then similar integral will be 5. And it's possible to give also asymptotic of this transition density with respect to x minus y. It has power tails, and in many senses, these transition properties of this Markov process similar to the properties of so-called stable, classical stable processes, which exist in any Euclidean space. But stable process exists only if some parameter alpha less than 2, but here parameter kappa or spectral dimension can be arbitrary. This is what can we say about X of and now we know a lot about operator L, hierarchical Laplace operator. We know a lot about corresponding process X of t. And the next natural step from the point of view of the function analysis is, or quantum mechanics is, to study Laplace Hamiltonian, which is negative L. Now, is a positive operator like in quantum mechanics, plus sigma. And again, I will take for simplicity the same u of x. I will take some random potential. This random potential might be defined for all x's. And the question is, how we define this potential in such a way that spectral analysis of this operator will be relatively simple. That's there are here two options. Several options is the situation when potential v of x omega is constant on the intervals of the fixed rank. There is such rank are not. Okay, z v of x omega equals sigma times x I, and here we have indicator. We have indicator of the interval on the interval I r of x, r naught of x. Now simply, for instance, for r naught is equal to 0, we divided x-axis into the unit intervals, and so on and so forth. And we have here values sigma x1, sigma x2, and so on and so forth. This way, constant potential. I will call such random potential finite rank potentials. This is not very far from the far from the operator for the function which discussed Anatoly Kochubey in his talk, because such we use here hierarchical distance to some extent. This is the simplest possible model. We can consider, of course, any other potential. For instance, we can consider potentials which are locally linear, something like this. Again, have some partition of the x-axis of the interval of the fixed rank, for instance, r not is equal to 0. And on such interval, we have linear function, but the slope of the linear function is the random variable. I don't want to write down some exact formulas for this potential. And let us concentrate on this first case. What is important here, that if we have, for instance, assume that R not is equal to 0. Let's consider on the interval, for instance, interval from 1 to 2. And let us consider some subinterval I, R, I, which belongs to the interval from 0 to 2. And let us consider on this interval our Haar function. Let's consider Haar function, how Ri of x. Now, as easy to see, this integration of this function outside this interval will give 0, and as easy to see, this still will be eigenfunction. I will get potential, but still now, nevertheless, this will be eigenfunction with sigma, which will be kappa to the power r naught, to the power r, because r now will be lesser or equal than 0. There is plus here because I consider negative, and plus sigma times xi. All Haar functions which are concentrated on inside intervals of our partition of the rank R naught, all such eigenfunctions or such Haar function are the eigenfunction, but only the eigenvalue will be shifted by the corresponding random variables xi. And such completely supported eigenfunction, Haar functions, which width is smaller than 1, because for R0 is equal to 0. All such functions form invariant subspace. In this invariant subspace spectrum, spectrum of Hamiltonian H consists of the geometric progression kappa to the power r, and this geometric progression, because r negative, will increase very fast, and around each of such eigenvalue, because xi is random, it can get many values using ergodicity. It's not difficult to prove that around each kappa to the power r, you'll get some impurity zone of the length C. This is the simple part of our operator. It's highly important here that potential locally is constant. But if the function, if we consider, I will call this L minus. L minus is a set of all eigenfunction I Ri are less or equal than 0, and so on and so forth. Corresponding eigenvalues are kappa to the power r, and shifted by random variables. If we consider L -1 to one complement, if you consider functions which are not localized, then such function must be constant on each interval R0. In this subspace, operator H will be already bounded. And this subspace can be considered if we glue together all points in such intervals of the rank R0. If we call that each such interval the vertex of new graph, then this graph corresponding to this part of the Hamiltonian will be so-called Dyson lattice. Exactly, Dyson studied lattice form of such operator. It's exactly what is shown here. And for lattice, for Dyson lattice, it was proven in the end of the 20th century in my papers and the paper of one of my students and student of Boykan Yakshich. It was proven that on the Sierpinski, on the Dyson lattice, for arbitrary coupling constant and for arbitrary spectral dimension, the spectrum is pure point. Corresponding eigenfunctions are slowly decreasing because operator is non-constant. As a result, we have in the first part the following theorem. Proof of the localization theorem of the Dyson lattice. Well, it's pure probabilistic. In my paper, it was assumption originally that V of x not uniform distribution, but have so-called Cauchy distribution. Cauchy distribution has fundamental property that class of Cauchy distribution is closed with respect to fraction linear transformation, not only linear transformation, which is true for Gaussian and many other laws, but for fraction linear transformation. And because of this fact, for Cauchy random variables, the Dyson model can be explicitly solved. But if not Cauchy, that after several iterations of this operator, we have some new potential which is almost Cauchy or close Cauchy. It's necessary to develop some kind of perturbation theory, which I don't want to discuss. Finally, we have the following theorem. One, that if for arbitrary kappa between 0 and 1, that is for arbitrary spectral dimension S greater than 0 and less than infinity. And for arbitrary coupling constant sigma, which is greater than 0, it can be small. The operator H of omega has 0-point spectrum. It means that for almost all omega, this self-adjoint operator has complete system of eigenfunctions. Eigenfunctions are not decreasing exponentially because their decay depends on the operator L, but this operator L is non-local operator with a slowly decreasing tails. And for this spectrum, it's possible to prove some other result. For instance, that this spectrum has locally Poisson structure, and so on and so forth. This was done in the recent paper by Benikoff and his student, using again our old results about Dyson lattice. Benikoff, the student, considered general continuous operator. I want to emphasize here that for unbounded operator H, operator H is unbounded because for negative R spectrum of minus L tends to infinity. For this unbounded, for the unbounded operator, we have here complete localization for high energies. That at the same time, Anderson conjecture was in the case of Euclidean space, of course. He did not discuss ultrametric spaces. Anderson conjecture was that in continuous case for low energies we have localization, for high energies spectrum is continuous. This is not true for the hierarchical model.
2 more minutes.
Say that in the more complicated potentials, for instance, this was a linear potential, which I introduced as a case number 2. We expect, this is work in the progress, but we expect nevertheless some kind of the Anderson phase transition. The reason is that if we consider, for instance, on the interval 0, 1, our operator H on the finite interval plus X, operator negative L plus X is a linear potential. And if kappa is greater than 1/2, it's possible to prove that this operator has absolute continuous part of the spectrum. Physically, it's not difficult to expect this fact because operator multiplicated by X on the finite interval has a standard absolute continuous spectrum, but operator minus L has discrete spectrum in this case on the finite interval, and its potential here is stronger. And this is the indication that probably on the full space we have still something like this. But nevertheless, it's very important that even here on the interval 0, 1, it's very important that kappa greater than 1/2, which is equivalent to the statement that SH is greater than that S.
You have reached 50 minutes.
But I finished already. Thank you very much. I don't want to continue. I have, it's exactly 50 minutes.
Yeah. So thank you very much. And we have time for questions and comments.